And it says it is setting it up, redirecting, and we should be live.
All right, live now. So we turn the time over now to Zoltan Lahosky for turning software into computer chips.
Yes, thank you very much. Let me share my screen, which should be on now. And thank you for all the interaction. Indeed, it's 2 a.m. here. Let's hope that I won't be slowed down by that, because I think what I have here for you is something really cool and something that expands something I want you to think of, something more that you as a .NET developer can do, because, well, as a .NET developer, you can write all kinds of software, of course, but you can actually also create logic hardware, computer chips. So let's jump into that. But before any further details, a little bit of interaction, apart from what we have already heard. I'm from a company called Lombic Technologies, and day-to-day we are actually doing web development, .NET web development with the open source CMS Orchard or Orchard Core. Now, if you are a .NET web developer, I highly recommend you check out Orchard Core. It's a great CMS and also an underlying framework built on ASP.NET Core, following the MVC paradigm. It has a lively community. It's great, and we develop applications with it, even for clients like Microsoft itself, or Live Nation, or the Smithsonian Institution. But when we are not doing some web development, then we are doing some research and development, like with our Hastlayer project. Now, before that, though, I would like to talk a little bit about you. So let's suppose that you are working on an application or in a field where you are doing some number crunching. And by number crunching, I mean some high performance computations in the areas of, for example, AI or machine learning, including the now quite fashionable large language models. Or you are doing some image or video processing for web applications, cloud applications, or even computer vision for robots, embedded systems, cameras. Or you work in finance and work on algorithmic trading applications, or perhaps in any other kind of application, you work related to data compression or cryptography or cryptocurrencies. Now, in these cases, you may bump into performance issues of your application. And there are a couple of steps that you can take, the usual ones, of course. First, you need to figure out where the app is slow, so you profile it and try to optimize the slow parts. But let's suppose that you have already done that. The next step, or one of the next steps, is to parallelize your algorithm. So instead of running everything on a single thread, you run multiple threads, or rather use an abstraction like tasks from the .NET Task Parallel library. Let's suppose that you have already done this as well. And finally, of course, you can use faster hardware or more hardware. So scale up, like in the cloud, or scale out. Now, let's suppose that you have already done that, or you have exhausted all the viable options here. So you can continue to throw money at the problem, but you are getting diminishing returns. So what else you can do here? Well, you can take a heterogeneous computing approach. And heterogeneous here just means that you are using multiple specific processors or multiple hardware accelerators specific to given domains. GPUs, for example, video cards are like that. If you have graphical computations, they are great. FPGAs are something like that as well. Now, let's talk about that last part a little bit, GPUs and FPGAs, because you may be wondering, what are actually FPGAs? Now, if you haven't heard of FPGAs before, the acronym FPGA means Field Programmable Gate Array. You can think of these as computer chips that can basically rewired on the fly. They can be reconfigured to kind of behave like any other computer chip. So, for example, if you want to have a chip that detects cats on images, you can configure an FPGA to do that. If you want a hardware accelerator for your video game, you can also configure an FPGA to do that, within limitations, of course, because these also have a certain given capacity. Now, even if you haven't worked with FPGAs before, I'm pretty sure that in some way you have already used them. For example, if you Google something on Bing or used anything in Azure, you have already used them, because certain Bing tasks are accelerated by FPGAs, and Azure uses FPGAs for hardware accelerated networking. And sometimes FPGAs are also used in household appliances like routers, or less household appliances like X-ray machines. And self-driving vehicles sometimes also use them apart from GPUs, actually. And since we are talking about pretty much hardware design, you need to be a hardware engineer to utilize FPGA. Now, to alleviate some confusions you might have, or the FPGAs usually also have some kind of visible circuit board. They have nothing to do with something like a Raspberry Pi. Raspberries also usually have a visible circuit board, but they are small computers, nothing to do with FPGAs. Arduinos, similarly, they are microcontrollers, not FPGAs. Although I've read of projects that bring together an FPGA and the Raspberry, and perhaps also I've seen something like that with Arduinos too. Now, why would you use FPGAs if you are in the software industry? Because if you're a hardware engineer, then you would use an FPGA for hardware emulation. Like if you're designing a CPU, you would use FPGAs to test that design before spending millions of dollars and actually manufacturing that CPU. But if you're a software developer, you care about computation. So let's compare these devices in a totally arbitrary, non-scientific, and approximate way, just to give you an idea. And let's talk about parallelism first. So how many things you can compute at the same time? And CPUs are on the lower end here, I would say, because on a CPU you can have something like 2, 4, 8, 32, 64 cores, and that's about it. That's the hardware level parallelism you get. Now on GPUs, they are on the other end, because GPUs can have thousands of little processing cores, although these are much, much simpler. And FPGAs are kind of in between, although FPGAs don't really have cores, so to say. But the level of parallelism you can achieve is roughly in between. Now, the complexity of programs is what you can run on these devices has a different order, because I would say CPUs win here. If it's a program, you can run it on a CPU. GPUs have a much more limited programming model. They can't just execute any software, so they are on the lower end here. And FPGAs are again kind of in between, although with an FPGA you are not programming a processor, you are kind of creating a processor. You are creating a processor architecture just for your algorithm. And because of that, FPGAs are really, really power efficient, because when it comes to power efficiency, so how many things you can compute with 1 watt of power, then CPUs and GPUs are roughly on the same level here, I would say, although this depends highly on your application and the specific hardware. But FPGAs are really power efficient because they just do what you need them to do. Everything is hardwired. There's no operating system to run. There's no instruction set for a processor. There are no other programs running. Nothing. Everything is just there on the bare metal. But there's a huge downside, and that's that while programming CPUs and even GPUs is doable and easy enough, FPGAs are really a different kind of beast. Because when it comes to an FPGA, you are designing a piece of logic hardware. You have to think in very low-level terms, like wires and logic gates and clock cycles it's super low level. But the computing benefits, the high level of parallelism connected with the high power efficiency makes it versatile. By the way, power efficiency doesn't just mean that we are saving the environment, but that's costs. Because when it comes to running things in a computing center, first you use power to run the computations, and secondly you use power to also dissipate away that heat, to cool. And if you can use less power, that's money saved twice. So FPGAs can be already versatile, but with tools like Hastlayer, we intend to bring the complexity of FPGAs development down all the way to the usual software development level. Because what is actually Hastlayer? You can think of it as a tool that takes a computer program and turns it into an equivalent FPGA logic. So you could also say that it takes a computer program and turns it into a computer chip. That's our tagline, but of course it's a simplification. What we are actually doing is that we take the logic expressed in a software form and try to generate some equivalent logic expressed as hardware form that computes the same thing. And of course, we are talking about not just any programs, but .NET. And Hastlayer indeed processes .NET, not C# or not any .NET language, but .NET assemblies. It decompiles .NET assemblies and generates the equivalent FPGA logic out of it. And this means that not just C# or Visual Basic can be used, but also C++ or functional languages like F#. We actually have an F# sample as well, or even scripting languages. So all in all, what we are talking about here is to get the computing benefits that FPGAs can provide for all of us software developers. So first, you get a substantial performance increase if your computations, if your algorithm is massively parallel and either compute bound and or memory bound. Secondly, you also get a higher power efficiency, which translates to lower operating costs. And thirdly, it's still software development as usual. So a lot of talk until now. Let's actually see this thing in action. Now I will switch over to Visual Studio. And this is the demo algorithm that I will run for you here. What I'm showing you here is, by the way, the Hastlayer SDK. It's fully open source up on GitHub. I will also show you the link to that later. And this parallel algorithm here, you may have guessed that it's a highly parallel algorithm. This is kind of an exaggerated example of the kind of algorithms that are especially suited to be accelerated with FPGAs by Hastlayer. And what it does is in this run method, and the core of the logic is actually here. Again, this is not a real-life example. We also have those, by the way. This is just a synthetic example. And what it does is that there's some conditional logic, which is repeated 10 million times. This is kind of a simulation of some arbitrary number crunching. And this whole thing here is started in tasks. I guess everybody here knows tasks, but if not, a task is kind of an abstraction over a thread. For now, you can think of tasks as threads. And we are actually starting this many threads, and this many is coming from a field, and it's 260. It's 260 because actually this many will fit on an FPGA. When Hastlayer processes the assembly of code, what will happen is that it will basically create copies of this algorithm 260 times on the FPGA. It will have an actual hardware level parallelism of 260. It's kind of like having a 260 core processor just for this class. And that's where all of the performance benefits come from. By the way, since we are using tasks and not threads here, this will be fine in .NET, meaning that we won't overload the CPU. We won't saturate the throughput of the CPU with too many threads. The taskbar library will take care of only starting as many threads as the CPU can handle. And pretty much that's the algorithm. There's some plumbing at the end to actually have an output of all of these as well, but that's the bulk of the code here. And let me actually run this. Now I won't run it on my PC, but I have something cooler here. This thing. This is actually the onboard computer of a satellite. So when you hear about CubeSats, little satellites that orbit the Earth or even orbit comets sometimes, or asteroids, then the smaller ones have something like this. This is actually a lot bigger than what goes onto an actual satellite, because this is a development board that has all kinds of bells and whistles, so I can also attach it to my PC, for example. But this is basically what goes on board of a satellite as well. It has a little ARM CPU, a 2-core ARM CPU, something similar to what you have in your phone. It runs Linux, and it runs .NET, and it runs Hastlayer, because it also has an FPGA in that ARM CPU that we'll utilize with Hastlayer. I will switch over to a terminal now, because I'm remoting into that little Linux on this onboard computer, and I've just started our demo app. Or demo script. What happens here is that first Hastlayer generates the hardware implementation. Then it starts to execute this mentioned parallel algorithm. First as software on that 2-core ARM CPU that I mentioned. And then it executes the same thing on the FPGA of this device 3 times. So we can compare the results. And this actually finished now, so we can check out the numbers. And the votes are in. When it comes to the usual software execution, it took around 25 seconds altogether. So this is a pretty long computation for the CPU. Now let's take a look at the hardware execution, and that's there's some debug outputs here and diagnostics outputs, and finally we can take a look at the hardware execution time, which was around 240 milliseconds when we just take the hardware execution itself into account. So what happened on the FPGA itself. But we are not just using the FPGA, we are actually running software on the CPU and communicating with that FPGA like we would communicate with the GPU, with a video card. And taking the communication round trip into account as well, it was around 330 milliseconds. It was a lot slower actually, because this is .NET and there was JIT compilation, there were caches that needed to be warmed up. But if you take a look at the second execution, it took exactly the same amount of time on the hardware itself, and it took around 263 milliseconds altogether. So roughly what we see here is that on the FPGA, the same algorithm took around a hundredth of the time. It was 100 times faster. Now, your mileage may vary, and this is, again, a synthetic example, but still it shows you what's possible. You can get, well, even 100 times speed up, but something like a 10 times speed up is quite doable as well. And you get the same thing with a lower power consumption, which again translates to lower costs. I've shown you an embedded device here that goes on board of a satellite because I wanted to show you something cool that you may have may didn't know about, that you can, as a .NET developer, actually develop apps for satellites. Now, on board of satellites, power consumption matters a lot. That's you have a small amount of power available, and you also have to cool that device. It's you want to consume as small amount of power as possible. But if you are running something in the cloud, the power consumption matters there a lot as well, which is again costs. FPGAs are also available in all of the major clouds too. One more thing about the code that I wanted to show you. This parallel algorithm here is well, really the algorithmic part of our application, but this is just a single class. This is not alone. So this would be part of a larger .NET application. How are you using Hastlayer from .NET? So if you have a .NET app, you compartmentalized the computationally intensive algorithmic part of it into a different assembly or into several classes. How you execute these classes on the hardware? Well, we also have an example of that here, and this is how you do it. Well, first you start a Hastlayer shell, and then comes some configuration. This is basically telling Hastlayer what's the class or what are the classes that you want to call from the outside, from the CPU. Where's the whole thing starting? And then there's the actual hardware generation part, which is this method call here. This method called generate hardware async is where most of the magic happens. This is where Hastlayer will create the hardware implementation from your .NET assembly, and also use a tool by the FPGA manufacturer to actually load this design onto the FPGA. And while you are doing that, you also have to tell Hastlayer which assemblies you want to use, or which assemblies you want to process, which is happening here. And finally comes the part why we are doing the whole thing, the execution. And what you see here is that, well, first, here's the test for the CPU execution. And here's where we actually use our parallel algorithm. And as you can see, what happens is that we take an instance of parallel algorithm and wrap it into a dynamic proxy with Hastlayer. This basically means that every method call to that parallel algorithm, to the instance of the parallel algorithm class, will be hijacked by Hastlayer. And depending on the configuration, it will transfer these method calls onto the FPGA. And this actually happens here. You see, we have 3 hardware executions here, and what happens is that you just call run. That's it. You call .NET methods with .NET types, and that's really all that's to it. Behind the scenes, Hastlayer will take this method call, pretty much serialize the inputs, send all the parameters to the FPGA. There it will start the hardware implementation of your code, wait for the results, send the results back, deserialize them, and what you get in the end is what looks like a .NET method call. So how cool is that? Now, you may be wondering that, okay, this looks like magic, but I'm pretty sure it is not actual magic. So how does it work? What's under the hood? Now, if you are really interested, you can check it out in detail, because again, the whole source code is up on GitHub. But let me give you a little bit of idea here. This is the device that I've shown you. This is the actual FPGA board, and the FPGA itself that, to be more precise, the ARM CPU and the FPGA, which is in a single chip, is the chip in the middle there. And that little thing goes into this bigger thing. This is the motherboard. This is the development board that I also show you. This is that you plug into your PC and into a power supply, so you can actually work with it. And let me show you also what Hastlayer actually generates, because I used simplified terminology until now. I told you something like Hastlayer generates the hardware design, the hardware implementation. It loads that in onto the FPGA. Now, to be specific, what Hastlayer actually generates is this code here. What you see here is hardware design, it's hardware code. It's written in the language VHDL, and it looks like some kind of program because, you know, we have something with package here. We also have a function and if else is, even return. So it looks like a programming language. Well, it really isn't a programming language. This is a hardware description language. Some of its aspects resemble a programming language, but it's a really different paradigm. You have to work in really different ways and think in really different terms. By the way, this was basically the most familiar part of the whole code file that I could show you, because if we scroll down a little bit, we'll see some real hardware code and also some familiar things, because if I scroll down here, we see something with the name parallel algorithm. Now that is familiar, and this block here that I'm showing you is actually just type declarations, you know, like what you write as fields or properties in a class, or when you declare variables in your inside a method. So this is not the whole picture, but why I wanted to show you this is because it has the index 0, and if you scroll down a little bit, we see exactly the same thing, but it has the index 1, and a little bit more to the bottom that has the index 2. Now, can you guess where I'm going with this? Well, of course, I mentioned you that we have 260 here in parallel algorithm declared as the degree of parallelism. This is how many tasks will be started in .NET. And I also mentioned you that we have 260 here because when it comes to the hardware implementation, we'll have 260 copies of this code. And this is what's happening here. So we are now at the index 242. If I scroll down a little bit more, we reach all the way down the index 259. So that's where all the 260 copies are. And copies, when it comes to hardware development, is a good thing because that means parallelism, that means performance, that means efficiency. We are basically looking at a 260 core CPU or 260 core processor that can only compute this parallel algorithm. It can't do anything else, but it can compute what's inside parallel algorithm really, really efficiently and with a really high degree of parallelism. And so that's where all the gains of FPGAs comes from. You can implement pretty much your own architecture. And the codes that you see here is something that usually hardware designers write. This is fully automatically generated though, but despite that, it's actually formatted and documented, as you can see. So these green things are comments, but still, it's quite a mouthful with something like 100,000 lines of code. So that was basically the most important parts of Hastlayer. What else is there? I've shown you an embedded device here, this onboard computer of a satellite. I also briefly mentioned the availability of cloud options. How this is possible is that we support, with Hastlayer, we support something called Xilinx Vitis. Vitis is a toolbox of the FPGA manufacturer called Xilinx, and we are using FPGAs of the manufacturer Xilinx here. Vitis basically helps you support multiple FPGAs with the same code. This is a huge thing in the FPGA world, because we as .NET developers are used to, well, writing our code, compiling it, and then running it pretty much anywhere. Or since .NET Core, that anywhere includes pretty much almost anywhere indeed. But with FPGAs, you don't just have to target specific FPGA chips, but you also have to target specific FPGA boards those chips are in. Again, it's super low level. But with Vitis, this is a little bit easier. We still need to support each device separately, but it's easier. And because of that, Hastlayer also supports cards that are available in the cloud, what Xilinx calls data center accelerator cards. Those are huge FPGAs, very expensive and very fast. And these are available in pretty much all major cloud computing providers: Azure, AWS, Baidu Cloud, and smaller clouds as well. And you can use them in your own data center, on premises, in your home PC even, as well. And because of this Vitis support, we can also target the aerospace industry as well. So again, you as a .NET developer can write applications that run on board of a satellite, or if you want to have something easier to reach than on board of drones. We have done some benchmarks, and the details of these are available also on GitHub. We benchmarked on the data center accelerator cards called Alveo cards, and on these satellite onboard computers. The data center accelerator cards actually brought smaller performance advantages and power consumption advantages compared to the cloud servers. So we are always, when it comes to FPGA benchmarking, it's always comparing apples with oranges, because you are comparing two completely different computing devices. But still, we compared a high-end FPGA in the cloud with a high-end CPU available in the same cloud. Specifically, this was Azure, I think. And we got multiple dozen or even more than 100 times speed or power advantage in some cases, or just a factor of 4 in less lucky scenarios. When it comes to the Zings, those are the satellite onboard computers. We had some even nicer numbers, but again, those are compared to the CPU on those Zings, on those onboard computers. So we are comparing a low cost, low power, low performance FPGA to a low cost, low power, low performance CPU to have it as fair as possible. And one interesting thing is that, again, you are kind of creating a processor for your application with FPGAs and with Hastlayer. And it also means that you can create your own number formats, and you will get hardware support for it immediately. This is what we actually did with a number format called POSIX, because you might not think of number formats because there's int and all the other integer formats in .NET. There's float and double if you want to have fractions, or there's decimal if you want to use decimal fractions for financial computations usually. But those are not the best for every use case. Actually, double and floats are built on a 30 or even 40-year-old standard now. And there are better options overall, and better options for specific use cases like machine learning. POSIT is a number type developed by a mathematician called Dr. John Gustafson, and we have taken his reference implementations, paper and white paper, and pretty much created a .NET library that has a POSIT number type. The advantage here is that it can have both a better range and a better accuracy than the floating point numbers you usually have in .NET, with the same amount of bits or even sometimes fewer bits. And that's also Hastlayer compatible. So if you also have kind of a POSIT processor now. If you want to have more use cases in the future, so if you have something that might need hardware acceleration, a .NET application in the mentioned number crunching use cases, then please let me know. I would be very happy to help you look into it and see whether it would make sense to add hardware acceleration to your project. We also partnered with the Wigner Research Center for Physics, which is a scientific institution, of course, because when it comes to scientific computing, performance also matters a lot. We are testing Hastlayer on scientific computations. And FPGAs are nowadays available in every major cloud, in big data centers all over the world. As mentioned, AWS, Azure already have them. And by the way, the CPU manufacturers also know that Moore's law won't go on forever, because there are physical limits. We can't put more stuff on the same chip now. And the architecture can't be much better either. So alternative ways need to be considered, and heterogeneous computing with FPGAs is one of them. That is why Intel bought Altera. Altera was the second largest FPGA company. And AMD recently bought Xilinx, which was the biggest FPGA company. So the two large CPU manufacturers bought the two large FPGA manufacturers. Now go figure. So if you like this, and I really hope you did, then please check out the SDK on GitHub. It's fully open source up there. You can check out the benchmarks in detail. You can check out more samples. There's documentation about how you can start and when using Hastlayer makes sense. And you can interact with the life of the project. And be ready, because I think FPGAs will be more prevalent in the near future. I would say that perhaps where we are with FPGAs nowadays is where we were with GPUs 10 or 15 years ago, because at the time, GPUs were just a playground of specialists. You use them if you were a video game developer, but general purpose computing with GPUs was not a thing. That started as a hack. And gradually, it got more and more support. And nowadays, you can just program a GPU for general computing as well. I think the same shift is happening with FPGAs. The availability in the cloud is one major sign of this. So thank you very much. Please get in touch with me if you have any further questions, or if you have a cool use case. Check out the project on GitHub, or check out lombik.com for the company behind Hastlayer, or if you are interested in Orchard, perhaps. And now I think we can have a little bit of a conversation as well.
Great. So Zoltan, are you able to see the questions that have been posted to the chat?
In Zoom, yes.
Okay, yeah. So we do have a couple of questions from Kelly. I'll go ahead and read them, and then you can read along with me, obviously. But once the Hastlayer loads the FPGA, is it stable? Your demo created the method, used Hastlayer to load it into the hardware, and then used proxy to run the method in the hardware. Does the program hardware stay resident if I unload the FPGA, put it on a shelf for a year, then move it somewhere else? Can I just run the proxy at that point and still have it work?
Mm-hmm. Yeah, some great questions, Kelly. Let me answer that first one, because there are actually three questions, I think. So the first question is that it depends. It depends on the configuration of the FPGA itself. It's possible. What happens, just to give you a little bit of an idea about how FPGAs work, is that there's an FPGA fabric, we call that, and its configuration is kind of the hardware implementation. And that configuration is usually stored, if you want to store it, in a flash memory chip. So that flash memory is written to when we load the hardware design onto the FPGA. And the flash memory can be volatile, or it can be durable. This depends on the specific FPGA, but the use case is possible. So there are FPGAs and there are configurations of FPGAs where you can do this loading of the hardware design. It's, by the way, called programming, but it's not that kind of programming, so that's why I didn't use that word. This programming happens once, you put the FPGA on the shelf, and it will be available in a year as well.
Great. Can the code in hardware be reverse engineered? If I've keyed a hashing function where I want to hide the key from the user, so I include the key in the code, can someone take the FPGA and get the key from it?
Mm-hmm. I'm probably not the best person to answer that, because I'm not entirely sure about the details, but I think the short answer is yes. Why I think that is because whole hardware designs can actually be encrypted. That means that that you can actually purchase hardware designs, components of hardware designs called IP cores in the FPGA design world. You can add them to your FPGA design, and you are not able to look into those designs. You just use them as black box components, kind of like having some kind of an encrypted or at least obfuscated .NET assembly. It's not obfuscation though. This is actually encryption. I don't know how it works because I'm not an FPGA developer. I'm a .NET developer who needed to learn a lot of FPGA development to work on Hastlayer, but we also have FPGA developers working on a project who actually know all of these in details. Okay. If you are interested, I can actually ask this specific question, but again, I think the short answer is yes. You can. Sorry, no. The short answer is no. Now I see the question. The short answer is no. No, the code cannot be reverse engineered, and the code and not just the key, but the whole hashing function can be encrypted in a way that it can't be reverse engineered from the FPGA.
Okay, so if I understood you right, there may be an extra step or something that you need to take in order to enable that, in order to ensure that the code could not be reverse engineered. Would Kelly, who's the person who asked this, would it be okay for them to email you and maybe get some additional resources or ideas about how that would take place?
Sorry, was the question to Kelly or me?
So the question is to you. Kelly is the person who asked the question about preventing the reverse engineering. And so I'm just asking that if they were to email you, would you be able to either provide them some additional details about preventing that, or put them in touch with somebody who could help them out with that?
Yeah, of course.
Okay.
Either in an email or or under the meetup events page, actually, in a comment. I will also follow up there. So yeah, for sure.
Okay. The last question that Kelly asked was, you said the gains from an FPGA come from parallelism. What if I have a process that cannot be parallelized, like hashing, like a hashing function that takes the output of the function and feeds it back into the function and runs it a million times? How much faster or slower might a Hastlayer generated FPGA be than a CPU for this process?
This depends, unfortunately, so I can't give you a proper answer. Usually in such cases, the FPGA implementation can be more power efficient. Now, whether that matters for you or not, that's a different question. When it comes to executing a hashing function and perhaps only just a few times, I would guess that it doesn't matter. If it's something that's executed a million times every minute, then perhaps yes. But usually where using FPGAs and Hastlayer makes sense is when you have some kind of parallelized algorithm, or you are really, really power consumption constrained, like on board of a satellite. Ideally, both. Now, that being said, this also highly depends on the hashing function itself, because modern CPUs can have a lot of magic happening to make things faster, even if something is single-threaded. But that also means that you can do quirky things in your code that will just be slow on a CPU. And we can also extract parallelism from your codes, even if it's single-threaded, but we can do operation-level parallelism. Together with that, and that's on an FPGA, you can do a lot more per clock cycle than on a CPU. Sometimes it can still be faster. It depends. One thing that I didn't mention is that FPGAs are running on much lower clock speeds, and so a CPU is or a GPU is in the order of magnitude of gigahertz clock speeds, and FPGA is in hundreds of megahertz. I think in the particular case of what I've shown you, the CPU is actually something around 800 megahertz, and again, it's an ARM CPU for embedded devices, and FPGA was around 150 megahertz or so. So while the FPGA is a lot more efficient per clock cycle, it also has a lot fewer clock cycles. It depends. The best way is to try.
Excellent. A question that I have is for somebody who's got a little experience with microcontrollers, working with Arduinos or working with the Parallax controller, there's some relatively simple kind of starter projects that you can do. Make a light controller or make a controller that measures the moisture in your garden and turns your faucets on to water your garden and things like that. Do you have a good suggestion for one or two projects for somebody who has that kind of experience, but who wanted to experiment with an FPGA? Some suggestions for some good kind of hobbyist starter projects.
Mm-hmm. Well, the most important thing you have in this case is your affinity for low-level stuff, and your will to tinker around, because otherwise, something like an Arduino or a Raspberry Pi is, as mentioned, quite different. Although being low power is one of the aspects, and sometimes it being an embedded system is also a similar aspect. Now, when it comes to FPGA development itself, so we are not talking about Hastlayer and .NET, but FPGAs, then there are similar examples. The classic example is a blinking LED. So something similar, or or actually measuring voltages from sensors. Basically, temperature is like that, is something like that as well, and managing buttons. What I've shown you as an FPGA here is a low power, low cost FPGA, but it's still one that's quite capable, and quite capable in the hardware acceleration space. That's what we intend to use it for. But if you are not talking about hardware acceleration, but you want to just tinker around with an FPGA, then there are even a lot smaller, lot cheaper options. In concrete terms, this board I have here is something around $200-300, I think. And as you have seen, it's palm sized, but you can get FPGAs that are smaller than a pen drive for like 15 or 30 bucks. And of course, you can get one which are huge cards, go into Azure data centers, and which cost $15,000. But for tinkering, you can get the small, cheap ones as well, and play around with LEDs or something, or buttons. To play around with Hastlayer, we have the samples in the SDK repository, which are kind of the best starting points. They are more complicated than managing a humidity sensor, for example, but I think still understandable.
Great. Well, I've got a drawer full of Arduinos and Pis, so maybe it's time to clean out a little space and get a hobbyist kit, an FPGA. These sound like they might be fun to tinker with.
Does Hastlayer provide abstractions or something for inputs, right? Like, say, I am working with a sensor, or I want to send a stream of data from a video camera or something like that.
Sorry, your voice was cutting out between does Hastlayer provide abstractions and then accessing a sensor like a video camera. What was in between these two?
Yes. So does it provide abstractions for the input, right? Like, in other words, if I wanted to read, voltage updates from a sensor, or if I wanted to send a stream of data from a video camera, how would we go about that with Hastlayer?
Mm-hmm. Unfortunately, there are no abstractions for these use cases. So what we are aiming for with Hastlayer is the hardware acceleration approach. So you have an algorithm that you want to make faster and or consume less power, less money, and yet exhausted the usual approaches. So because of that, the kind of the API that we provide is geared toward that as well. It's basically about passing data between what runs on the FPGA and what runs on your CPU. Now, what you are talking about is more of a completely independent embedded system. That's, by the way, one use case of FPGAs as well, where you don't have a microcontroller, where you don't have a little computer like a Raspberry, but you have an FPGA, and that's what's sitting on an IoT device, for example, and that's reading sensor data, communicating on a network, etc. That's actually also possible with Hastlayer, but it's a use case that we don't really specifically aim for. There are no things that would make it easier for you to communicate with these peripherals. There's a memory mapped API pretty much. So think of the old days of memory mapped peripherals as well, which are still the case, just we are not working with them directly. That's what happens with Hastlayer as well.
Okay, thank you.
Right, thank you very much for all discussions. Really exciting.
Yeah, any other questions?
And köszönöm, Kelly. It was thank you in Hungarian.
Excellent. That's probably the first Hungarian comment we've had in this group. All right, Caleb, do you want to go ahead and end the YouTube stream?
Yes, I will do that.